group did our research on the fundamental theorem of finite abelian groups. Now what is that? The theorem states, let G be a finite abelian group, then G is isomorphic to a direct product of cyclic groups. Of course, this is obvious for cyclic groups, so let's examine the smallest non-cyclic abelian group. That's the Klein 4 group. Interestingly enough, this group is isomorphic to 2z cross 2z. This raises the question, is this a way to classify finite abelian groups? In fact, it is. This theorem gives us a way to classify all finite abelian groups. For example, given any positive integer n, we can use this theorem to list all abelian groups of order n. And an example of this is if n equals 12, then there exists only 2 groups that are abelian that are isomorphic to it. Again, this is because finite abelian groups can be written as a product of cyclic groups. A way to visualize this is if we have a group G that is isomorphic to the direct product of 2 cyclic groups, then we can generate all of G by having one of those cyclic groups acting on another and looking at the orbits. Visually, this will generate a torus that is isomorphic to the original group G.
Before we start the proof of the fundamental theorem, we will take a look at 2 lemmas that will help us in proving the theorem. The first one is if G is a group and H1 through Hn are all subgroups of G with the product of all the subgroups equal to G, and if every G and G can be written uniquely as a product of the H's, then given any 2 subgroups Hi and Hj, their intersection is the identity. In this proof, we're going to create a mapping, which is the canonical homomorphism 5 H1 through Hn equal to the product of H1 through Hn. Since G can be written uniquely as a product of H's, it clearly follows that phi is injective. Now, if X is in the intersection of Hi and Hj, then it is in X is in Hi and it's in Hj, so they each have inverses. And if we define A to be equal to Ex, X inverse, which is in the cross product of all the H's, and B similarly just flipping the X and the X inverse, and we take 5A and 5B, we see that they're both equal to E. Because phi is injective, it follows that A is equal to B, so X is equal to X inverse, which means that X must be E, so the intersection must be E. And the conclusion that taking any 2 subgroups and taking the intersection will give you the identity also leads to the conclusion that if you take one subgroup out and you intersect it with the product of all the remaining subgroups, the intersection is also E.
We can visualize lemma 1 by using the torus yet again. Let H and K be 2 subgroups of G such that H times K equals G, and every little h and every little k get multiplied to get a unique element of G. By examining the orbits of K when H is acting on, it demonstrates that no orbit will intersect with any other orbit except at the identity element. The torus visually represents these orbits and thus the entire group G.
Okay, the second theorem will sort of serve as the outline for our actual proof, and it requires 3 conditions. One, that G is equal to the product of the subgroups A1 through AN of G, and if you remove one arbitrary subgroup and intersect it with the product of all of those, then the intersection will be the identity. And finally, that each subgroup is also normal within G. However, since G is abelian, it directly follows that each subgroup A is normal in G. And using these 3 conditions, we can create an isomorphic group of the direct product of the subgroups to G. And this will be the theorem that we use to sort of outline our whole proof. And the second 2 conditions, that G is equal to the product of the subgroups and that the intersection is E, will be claim 1 and claim 2 for this proof.
Now we're going to go on to the proof of the fundamental theorem of finite abelian groups. First, let's restate the theorem. The fundamental theorem of finite abelian groups says that for any G that is a finite abelian group, there is a direct product of cyclic groups isomorphic to G. So to prove this, we're going to use strong induction on the order of G, where G is a finite abelian group. Our base case says that the order of G is equal to 1. Now, obviously, if the order of G is equal to 1, then G is just equal to the group containing only E, which is equal to Z mod 1Z. Our inductive hypothesis says, assume that the order of G is greater than or equal to 1, and the theorem holds for every abelian group with order less than G. Now, let little ai be in G be an element with maximum order. In other words, it has the largest order that's not equal to the order of G. Now let big A1 be equal to the set generated by little a1. A1 is normal because G is abelian. Therefore, G mod A1 exists. Now to find pi to be the canonical homomorphism from G to G mod A1 by pi of little g is equal to the right coset A1 plus G for all G in G. Since the order of G mod A1 is less than the order of G, we have by our inductive hypothesis that G mod A1 is isomorphic to a direct product of cyclic groups H1 through Hn. Now you're going to define Hi with little tilde on top to be equal to the direct product of E in H1 cross E in H2 cross dot 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 cross Hi cross dot 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 cross E in Hn. So with this definition for H with a tilde on top, G mod A1 is equal to H1 with a tilde, H2 with a tilde, times dot 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 Hn with a tilde, where Hi with a tilde is isomorphic to Hi. So since Hi with a tilde is cyclic, we have that Hi with a tilde is equal to the set generated by some Hi, where Hi is in G mod Ai. This implies that there exists an Ai in G such that pi of Ai is equal to Hi, and the order of Ai is equal to the order of Hi. So now we're going to define big Ai to be equal to the set generated by little ai. Therefore, the order of big Ai is equal to the order of Hi with a tilde on top.
So now let's start with claim 1, which is that G is equivalent to the product of the groups A1 through AN. Proving the first direction of inclusion is intuitive, so I'll just skip that for now. So to prove the opposite direction, let G be an element of G. We know pi of G is an element of G mod A1, and G mod A1 can be written as the product of the groups generated by little h1 through little hn. Therefore, pi of G equals h1 to the k1, h2 to the k2, through hn to the kn. Define x in the group G such that x equals G times a1 to the negative k1 times a2 to the negative k2, all the way up through an to the negative kn. Now pi of x equals pi of each of those terms multiplied together, since pi is a homomorphism. This equals h1 to the k1, h2 to the k2, through hn to the kn, times h1 to the negative k1, all multiplied up through hn to the negative kn. It's clear to see that this is equal to the identity. Therefore, x is in the kernel of pi. We also know that the kernel of pi equals a1, because for any g in a1, the coset a1 plus g is equal to the coset a1 plus e. So we have that x is in a1. Recall that x equals this. We can rearrange this to show that G equals x times a1 to the k1 through an to the kn. This implies that G is an element of the product of the groups a1 through an. Therefore, we've proven claim 1. Now let's look at claim 2. Claim 2 states that if you take out any ai and intersect it with the product of the rest of them, the intersection is trivial. Now I'll prove claim 2. Let x be an element of that intersection. Therefore, x can be written as ai to the ki, since it's an element of ai, or it can be written as a1 to the k1 times a2 to the k2 all the way up through an to the kn. It is easy to prove that this expression of x is unique. So by lemma 1, which stated that if G can be written uniquely as a product in this way, then the intersections of all of the subgroups is trivial. We have now shown that claim 2 is true. So to recap, we have shown in claim 1 that G is equal to the product of cyclic groups A1 through AN. Also, we have shown in claim 2 that if you take out any AI from that product and intersect it with the product of the rest of the subgroups, the intersection is trivial. So now we have, by the theorem, that G is isomorphic to the direct product of A1 through AN, all of which are cyclic subgroups, QED.